We're going to start off with the main door. From the exterior, the door is opened with a large handle. This handle is mimicked on the inside to close the door once all the passengers have boarded the plane. The handle turns the pins that hold the door closed while taking off. However, once at altitude, the pressure difference is the primary way the door is kept closed. Although the door does swing outward, it first pushes inward and to the side before swinging outward. This is so that when the door is closed, the pressurization in the fuselage pushes the door onto the frame of the plane, sealing the interface. This allows high pressure to help seal the door in flight conditions. Higher altitude gives higher gauge pressure. The door is supported by large hinges that allow the door to move inward, then outward, so the door may be opened in a convenient manner, while allowing it to be sealed by the pressure difference. Next up are the pilot windows. These are the windows that are in direct flow path of the oncoming air. These need to be the strongest windows on the airplane. In fact, these forward-mounted windshields need to be capable of withstanding the impact of a 4-pound bird without penetration at a velocity equal to the cruise of the airplane at sea level. The windows are a laminated multi-ply assembly, comprised of a minimum of 2 structural layers. These structural layers are typically made from strengthened glass, either by methods of thermal or chemical means, or polymers such as acrylic and polycarbonate. Apart from the structural layers, the cockpit windows include the protective facing plies to help mitigate the effect of scratches from use. The final components of note in the cockpit windows are the electroconductive wires. These wires are used as a heat source to prevent the windows from icing over and thereby preventing obstruction of the pilot's view. Next up are the passenger windows. The passenger windows have a curved nature to them, despite being moderately rectangular. If the windows were to have corners, there would be stress concentrations on those corners. As these windows are not experiencing the same pressures as the forward windows, they do not have to be as robust as the windshield, and thus require fewer layers. The cabin windows only consist of 3 distinct panes: the outer, middle, and inner panes, along with the required protective coatings. Generally, the structural panes are made up of the same acrylic that is sometimes used in the forward-facing cockpit windows. The outer pane is the main load-carrying component of the windows. It is the main barrier between the low-pressure, high-altitude air and the pressurized interior cabin. The middle pane is the second structural layer, and it serves as the fail-safe layer. As the name suggests, it is responsible for carrying the load in the case of a failure in the outer pane. The inner pane is a non-structural layer. Its primary purpose is to protect the middle pane from damage from passengers and serves as a barrier between the two. Also in the cabin area are the side emergency doors. The side emergency doors are somewhat similar to the main doors in the way they're sealed. When in the closed and locked position, the doors are pressed outward by the pressure difference. The emergency exit doors are placed on the aircraft in locations that allow a flow of passenger traffic to exit quickly. Emergency exit doors become detached when the emergency mechanism is utilized. The opening mechanism is a rotating lever that disengages the hinges, allowing the door to be lifted up and away. This allows the doors to be moved out of the way of exiting traffic in the case of an emergency. These doors weigh about 40 to 50 pounds, so a moderately fit person should be able to remove the doors without complication, especially with adrenaline helping since it's an emergency. Next up are the cargo doors. The cargo doors are accessed from the exterior of the fuselage while the plane is grounded. These doors open upward and inward and are locked open by locking the interior door in place on top of the exterior door. This can be seen in the provided picture. When closed, there is an interior door that comes down to prevent luggage from blocking the door from being opened. Both sections of cargo space are pressurized, but only one is environmentally controlled and is able to transport animals. Now on to the aft bulkhead door. The design is similar to the main passenger door, but the main difference is that it's not a double-hinged door, and thus only rotates on one axis. Also, this door is not intended to be opened in an emergency situation. History can provide invaluable insight about how pressurized aircraft should be designed. Whenever proper attention is not placed on the design, failures can occur. One of the most famous examples of failed pressurized components occurred in the de Havilland Comet. In the span of just 1 year, 3 comets had inexplicably crashed, killing everyone on board. To determine the cause of the crashes, an entire fuselage was placed in a specially designed tank, and the fuselage was pressurized with water to approximate flight pressure conditions. The pressure was then cycled to simulate the lifespan of the aircraft. After about 3,000 pressurization cycles, including the preceding flights taken before the tank tests, the fuselage failed. Upon the examination of the failed fuselage, it was determined that the failure originated at one of the windows. The Comet incorporated square windows into its design due to the immature knowledge of pressurized air travel. These square windows introduced stress concentrations that the designers did not account for. It was at one of the corners of the windows, where the stress concentrations are the greatest, where the failure began. Here, the designers did not pay close enough attention to the design of the windows, and due to this, the aircraft failed to meet expectations. Because of the de Havilland Comet's failures, manufacturers learned how important that window design is when designing new aircraft. Because of the de Havilland Comet's failures, manufacturers learned how important that window design is when designing new aircraft. Due to this, all manufacturers began incorporating rounded windows to reduce the stress concentrations, and thereby increasing the life of the aircraft.